Hi, this is Al, your probability and statistics instructor. Okay, time to begin doing some probability. In this video, I would like to talk about the following theorem, the following result, Bayes' theorem. We are going to be revisiting this theorem in the future. So that's why I gave this video the title Bayes' theorem part 1. Okay, we're going to play around with it again. Well, to begin this introduction to Bayes' theorem, we are going to solve a problem. That's a problem we are interested in solving. Okay, there's an insurance company, and these guys have divided their policy holders into two different groups, two mutually exclusive groups, smokers and non-smokers. It turns out that for a randomly chosen non-smoker, the probability of dying during the year is 0.01 or 1%. On the other hand, for smokers, the probability of dying during the year is 5%. So, the problem we want to solve is this. Given that a policy holder has died, what is the probability that the policy holder was a smoker? Make sense? Okay, so just as we have been doing it lately, let's use our fancy notation. Let us define our events of interest and translate the information from the problem into mathematical terms. So our problem, step number 1, let's define those events. S for smoker, N for non-smoker, and since we're going to be using a capital S for the event smoker, let me just remind you that we can use a different letter to refer to the entire sample space. I don't want to have any sort of misunderstanding here. S will be the sample space in this particular problem. Okay, that omega, that capital Greek O, can also be used to represent the sample space. Okay, let's keep our translation. Let's go back to the information that we had. We need those probabilities. We need the probability for dying. We need the probability of dying. We need the probability of a smoker. We need the probability of a non-smoker, and so on. Okay. So 10% of the company's life insurance policy holders are smokers. So probability of S is 10%, which means that the probability of non-smokers is going to be the complement, which means 90%, right? Something else, another important piece of information that we have here is that for each non-smoker, right, given that we have a non-smoker, the probability of dying is 1%. On the other hand, if given the information that we have a smoker, we have that the probability of dying is 5%. Okay, so let's record that. Also here we need dying as an event. So we said probability of being a smoker 10%, probability of non-smoker 90%. We also had that probability of dying given smoker was 5%, and probability of dying given non-smoker only 1%. Now let's find out what's the probability that we want. What is the probability that the policyholder was a smoker, right? But the thing is that it's a conditional probability. It is not one of those regular probabilities. Given that a policyholder has died, given that event, what is the probability that the policyholder was a smoker? So if we translate that, what we have here is, what we want is the probability of S given D. Okay, we have observed the occurrence of the event D. What's the probability of S? Right? Solution. Here we go. First, this is what we want. A conditional probability. So a good starting point would be writing down the definition for that conditional probability, right? And from a previous video, we know what's the formula for that conditional probability, right? Let me remind you. So by definition, probability of S given D equals probability of S and D divided by the probability of D. Makes sense? Probability of S and D divided by probability of D. If we could find those two numbers, the one at the top and the one at the bottom, the one on the numerator, the one on the denominator, we're done. Okay, so we neither have the top part nor the bottom part. So we have to find a way of finding those probabilities from the information that we've got. Okay? Note something. We have these conditional probabilities, and these conditional probabilities involve intersections, right? since we are interested in the probability of S and D, the one that has those two ingredients, those two events involved, would be this. Make sense? So let's use the definition in combination with this and see what happens. Okay? Okay. Let's write that down. Note that the probability of D given S is probability of the and S divided by the probability of D. But probability of D and S is the same as this, right? Oh, and this should be S. Probability of D and S is the same as probability of S and D. Okay? Then what we are going to say is solving for this guy. This is the one that we want. The one at the top, the intersection. Oh. What we have is probability of the given S times probability of S equals probability of S and D. So probability of S and D equals probability of D given S was 0.05 and probability of S 0.1. Make sense? .05 times 0.1. So we have the numerator. We just have to find the denominator and then we're done. The denominator that we want is this, the probability of D. Okay? How do we find that guy? Well, we will observe something. Observation. The entire sample space equals the union of smokers and non-smokers. You guys agree? Something else. Note that S the intersection between S and N equals the empty set. So we have two events, S and N, that together their union equals the entire sample space, and on the other hand their intersection, S and N, equals the empty set. You remember that we have a special name for that sort of events? We call them the compositions or partitions. So S and N form a partition for the sample space. Interesting, right? Okay. So note that the denominator that we are after is the event, well, the probability of the event D, dying. So we are going to do something here that at first looks kind of tricky, but then you'll see, oh, yeah, it makes sense. So we want the probability of D. That's the bottom part. D, the intersection between D and the sample space, equals D. You guys agree? The intersection with the entire sample space, it's going to be D. Okay. On the other hand, we said that we could rewrite, we could re-express the entire sample space in terms of those two events, being a smoker or a non-smoker. So the intersect S union N using distributive properties of union and intersection. Let me write this down. What we have is probability of the intersection S and then union the intersection N. Okay, makes sense. Distributive properties. Here, note something. It can be shown that the intersection S and the intersection N are mutually exclusive. Mutually exclusive. And property 3 of probability functions. Remember that if you want to find the probability of a union of mutually exclusive events, then it's just the sum of these individual probabilities. So what we have is that the probability of D equals probability of D intersected with S plus probability of D intersect N. Okay, makes sense? Okay. We are almost there. We want these, the probability of these two intersections, to find the probability of D. This one, guess what? We have already found it in terms of the information that we have, right? In terms of these conditional probabilities that we have. So we apply the same trick that we applied for probability of intersection between S and D for probability of intersection between D and N. Right? And we are done. Right? So this happens to be, we already know this first term, the probability for that intersection is 0.05 times 0.10. The other one will be the multiplication between the probability of dying given non-smoker times the probability of non-smoker, right? Which is going to be 0.01 times 0.9. Finally, the probability that we wanted, which was this probability of S given D of smoker given dead, will be this 5% times 10% divided by this. And if you do the math, that turns out to be just 5 divided by 14, and if we use R, 5 divided by 14 happens to be roughly 35%. Okay. Problem solved. Summary of what we just did. So what we did is we discussed something very important here. Bayes' rule. Note that what we had initially as part of the information that we had was the probability of D given S, but the one that we wanted was the probability of S given D. So we wanted those two events to switch places. We wanted to, some people say we wanted to reverse that probability. So when you want to reverse a probability like this, you have to use Bayes' rule, which is basically using a combination of the definition of conditional probability to find the numerator of this expression, and then using that trick, that decomposition, that partition of the sample space, and using again the definition of conditional probability to find the probability of these intersections. Okay, this is a particular case, an application of that rule, of that important theorem, Bayes' rule, and we're going to be using that theorem, that rule, when we're interested in reversing probabilities, conditional probabilities. Make sense? Okay, so that's it for now. Take care. See you next time. Keep working hard. Bye.